Hi everyone. I apologize that this lecture is a tiny little bit late. It's been madness here. I'm really excited about this lecture. The very first year I taught, the way the kind of curriculum laid out, I jumped in teaching structures 2. So it was students that hadn't had structures 1 from me, but someone else. I was given their course outline, but it didn't really match with what they had actually taught. And this was the second lecture that I gave, and I hated it. And in fact, this says lecture 2, but it's actually lecture 3. So I will fix that in the slide for you. So I'm just going to change that to lecture 2, lecture 3. And I hated this lecture. I hated giving it. And over the years, it's turned into one of my absolute favorite lectures. So this is one where you start to learn really new things. Things that you've heard about, and you use them in regular, everyday language. But as soon as I try to talk about it, you get all kind of flustered about it. So I want you to stop and remember every time I introduce something that everything you already know, everything you need to know about structures you already know. And so I'll try to relate most of this lecture to those things, to try to just remind you what's going on. Again, trying to get you to do the math, which is what we have to do, is really hard. So trying to find simplified examples that also relate to real world, that also have numbers that will help you out, is a really difficult challenge. So we'll go through these and then we'll jump into some examples that kind of align more with structural work. So in today's lecture, we're going to talk about the principles of stress and strain. And it's the easiest to talk about in axial applications. So what we're going to be talking about is an elemental block within our big object. And that's really what stress and strain is about. And so we're going to introduce a bunch of new things that you've probably heard the terms, but maybe aren't quite sure how they fit into what we're doing here. Actually, I also wanted to point out my kids are still home. We never got a positive COVID test. I was very much sick over the weekend. Tuesday was the day they were supposed to return back to school. Monday night, Malcolm and Duncan both got a fever of 101, which, because we had never had a positive, to assume that they actually had COVID before, we now had to reset our isolation. So as of Tuesday, we were re-isolating. So Tuesday, Wednesday, today's Thursday, day 3 of round 2 of isolation. So hopefully next week gets a little bit easier because a lot of things come back online next week. And I think in 2 weeks, the very first day, actually next week, you're getting a lecture. For those of you that are also in studio, you're getting a bonus lecture from Dave that I've created that kind of ties into your studio projects. But I will be posting it online, so those that aren't in studio are more than welcome to watch the video if it's of help to you as well. So I apologize. I will be coughing and possibly sneezing and sniffling a lot through the lecture, so I apologize for that. So we've talked about this before, the types of forces. Just a quick refresher here. We've got our axial forces, where tension is pulling it and compression is squashing it. That's a very linear force. People tend to really get their head around that. Shear is the one that messes everyone up for some reason, but it's about 2 planes slipping past each other. And in every object, we have a series of planes. So these 2 slip, and these 2 slip, and these 2 slip. And you can really look at that as a series of planes, and you can talk about some distance between them if you wanted to, acknowledging that it's just a whole bunch of those kind of stacked together doing that. Bending, we know, is this act of putting one side in compression and one side in tension. And torsion is that twisting action, We don't really get into that in structures 1 and 2, but it's nice to know that it's kind of part of the verbiage that we use for things, and it is something engineers check. All right, our axial forces, we remember, compression squashes it, tension stretches it, and we lump them both together, compression and tension, in our axial loads. Shear, there's that slipping action here. Now we've been drawing it as slipping this way, but you could do it that way if you wanted. You could turn that block and shift it the other way. Bending and torsion. Okay, what are stress and strain? We've been talking about force and deformation or deflection. In fact, I'm going to change strain to deformation. I'm going to say slide 7. I'm going to change strain. Well, I'm going to check. I'm going to check what I have in your assignment. But deflection or deformation. Okay, so stress and strain are to a material what force and deflection are to an object. So this is our object. We were seeing a force applied, and we were seeing deformation. Stress and strain is talking about the little block of material. So we don't need to know what the overall object is necessarily. We're talking about the little tiny block within our object. So stress and force can be exchanged, and strain and deflection or deformation can be exchanged. So let's take a look at what that means. And like I said, it's best to learn with axial forces. It's the easiest way to talk about this. So we've looked at objects with a force on it. We're going to talk about a compressive force, just because it tends to be an easy one. We're going to ignore buckling. We know that this tall, slender object would actually buckle, but we're not talking about that right now. We're just talking about the object with force. We know that it's going to squash. What we're talking about is a little tiny block within it, and how that force applied to the top kind of spreads out uniformly through the object and acts as a load, an internal force throughout the object. So object with force, 1 unit area of material with stress. So these two things are related to each other. Strain versus deformation. We have this object and it deforms. There's a force on it, but what we really care about is this deformation. We had an original object and we have deformation. It's the same as 1 unit area of material showing strain. So when it's the object, it's deformation or deflection. When it's the material, it's strain. So stress is defined as force per unit area. I've got quite a few typos in this one. Slide 10. As. Okay, so stress is defined as force per unit area. So it's like we take that force and we spread it out evenly over the unit area. Remember how we said that we could have a person on a 1 kilonewton point load on a 1 meter by 1 meter square, and we could relate that into kind of a surface pressure? Well, stress is very similar to that, except we're not going to work in kPa. I'm going to throw you off here. We're going to work in MPa. So MPa is newtons per millimeter squared. So if it's newtons, our force now wants to be in newtons, not kilonewtons. So this is a good way to remember it. When we're talking about force and deformation, we're usually talking about kilonewtons and meters, unless we're talking about the exact amount of deformation, and then often we'll put it in millimeters. Stress and strain, we almost work exclusively in newtons and millimeters. But they relate back and forth so easy. That's the beauty of a base 10 system. Don't get Dave started. He believes a base 6 system is the way the world should be run. We have debates about it. He's teaching our children to function in a base 6 system. So stress is defined as force per unit area. This is our symbol for stress. Get used to this. We've got all kinds of Greek letters coming at you here. Stress equals force divided by area. And so what we do is we take this force that was on our object over the area of our object, and then we could figure out what that stress is on any little tiny blob of the object, of that material within the object. So stress in newtons per millimeter squared, or what we would call MPa, force is in newtons, and cross-sectional area is in millimeters squared. So not kilonewtons and not millimeters squared. Let's take a look. If this is our object with an area, and this is our force P, it's the same thing as taking this force and smearing it evenly over the object, or our force divided by area. What happens if we have the exact same force over half of the area? Well, force divided by 1/2 area, what do you think? Do you think there is more stress on this object or less stress? And this is where I always say stop and do a gut check. The example I was going to use is an example we actually do for a math calculation in just a minute. But start and math. Anyway, do you think if we take the same load, okay, if you were trying to think of a great quick object that doesn't give away the next set of calculations. All right, if you're pushing on something with a certain amount of force, you don't change the amount of force. If you make that object half the size, do you think it's easier or harder to squash that thing? Well, you reduce the area. If you're pushing with the same amount of force, it's the same as, oh look, I'm a little bit in the way here. It's the same as our force divided by half of our area, or P divided by 1/2 A. We can rearrange this, and it's really 2PA. This is stress. So let's say our stress is P divided by A. If we have half of the area, it's the same thing as 2 stress. So this is twice as much stress as this version of it. Same force, half the area, twice the stress. What happens if we have this same system? So this is stress. We have half the force and half the area. Well, half the force and half the area is stress. So this is why it's great. We can take it down to the material size of the object. So we can go down within the object and start talking about what's happening internally. All right, let's do an example. I'm trying to decide if it's worth turning my camera. I've somewhat fixed it. This one's an easy one. So we'll start with this one verbally. We'll do some where we actually turn the camera down. So we've got Shannon in Bluntstones. So I took my Bluntstones, and for these 3 examples, I'm assuming I'm standing with both feet, not walking, kind of just standing flat down. There is a question on the assignment where we assume somebody's walking, and there's that moment where just their heel would be on the ground, and that's going to be relevant when you read the assignment question. And in that one, I'm very explicit that we're talking about just a heel being in contact with the ground. But this one, we're assuming somebody, it's the photo op. So I don't know if any of you have ever worn heels across a grass area, maybe to get your photo taken. I always think of wedding pictures, kind of being in a wedding party and trying to walk across the grass. You have to walk on your tiptoes because you know your heel goes down into the grass until you get where you need to be, and then you can stand there easily and get your picture taken. Okay, so we've got Shannon in some Bluntstones. I'm going to tell you that I weigh 600 newtons, or 0.6 kilonewtons. So we've taken that 0.6 kilonewtons and converted it to newtons. The area of my Bluntstones is 240 millimeters by 75 millimeters. So almost 10 inches by 3 inches. and I've got 2 feet standing there on the ground. So we've got 240 times 75 times 2 equals 36,000 millimeters squared. So we've got 600 divided by 36,000 millimeters squared, and we end up with 0.0166666666 MPa. Not KPa, MPa. Units start to be very, very, very important here. We're going to want to really pay attention to what unit of measurement. Remember, in the assignment, I always tell you what units I'm looking for, and I usually give you a pretty good hint of what the range of the answer is in that, and it'll should be to this many decimals. So I usually give you some pretty good hints about what that answer should look like. Okay, so our stress for Shannon in Bluntstones is 0.0167 MPa. What do you think? Shannon in heels, more or less stress on the ground? Well, you know that if you're walking in your heels, you punch through the ground. So let's ignore the heels for now. We'll assume I'm standing, and this is the surface area. So I've got the same amount of load. I haven't changed weight. I am still 600 newtons, but the area of my foot that's in contact with the ground has gone down. Instead of almost 10 inches long, it's only 4 inches long by 3 inches. So still 2 feet. I've got, are you in your running shorts? Would you like me to pause this? Sorry about that. He doesn't like anyone to see him in his running shorts because they're spandex and he feels very self-conscious. So, and then also in that time frame, he knocked over a full glass full of water, so I had to clean up glass and water. But the kids are in the basement and he's going for a run on the treadmill, so I have a few minutes of peace, so I'll finish recording this lecture. Okay, I'm now wearing my high heels on the grass instead of my Bluntstones. So I've got a smaller area of my foot in contact with the ground. So we're just talking about the front here. Remember, the assignment is slightly different, so read the assignment carefully. So I've got a smaller area. What do you think? Is the stress going to increase or decrease? I think you all know that the stress should increase. So we've got 600 divided by, and I'm going to use my brackets, 100 times 75 times 2, end bracket, 0.04 MPa. So we've got a higher stress. That makes sense. Now, for those of you that are living in Toronto, know about the big snowstorm that we had last week, and this is what our family has spent a lot of time doing, is snowshoeing. I'm still blocking this screen. So you intuitively know that you use snowshoes to lessen your stress on the snow surface area. You know that. Intuitively, you know that the bigger the area, the less the stress. Same force, increase the area, decrease the stress. So like I say, everything you need to know about structures you already know intuitively. All right, so we've got snowshoes that are 1 meter by 150 millimeters, or 6 inches. My weight hasn't changed, and I'm standing there getting my picture taken. So now we've got 600 divided by, and we've got 1,000 times 150 times 2 equals 0.002 MPa. So a lot less stress. High heels, highest stress. Bluntstones, the medium amount of stress. And the snowshoes, the least amount of stress. Remember, what we're trying to do with the snowshoes is not break through the surface of the snow. So intuitively, I think you know most of this. Okay, what's the stress an elephant exerts on the floor if it weighs 44 kilonewtons and its feet are approximately 500 millimeters in diameter? And yes, I did research on what an average elephant weighs and what the approximate diameter of their feet are. Okay. I'm going to turn my screen, I'm going to turn this down. I think this locks in place now. Yeah, I've got that fixed somewhat. Okay. So let's take a look at what we've got. We know what the force is. The force is 44 kilonewtons. But we know that we don't want to work in kilonewtons when we're talking about, I just realized I don't have my mic where I should. I hope you guys have been hearing this okay. I'm just going to move my mic. Some of you might notice an increase in sound or hopefully better sound quality. My mic, it's in the way most of the time. Okay, so our force is 44 kilonewtons. We want to change this into newtons, so it's 44,000 newtons. We know what our area is. Our area is 4 times the diameter of the four of the feet. So we need 4 times pi r squared. That's the area of a circle. We know what the diameter is, and we know that radius is half of the diameter. So we have 4 times pi times 500 divided by 2 squared. Let's calculate that. We've got 4 times pi times 500 divided by 2 squared. And we get 785,398 millimeters squared. We know that stress is force divided by area, or 44,000 divided by 785,398 millimeters squared, or 44,000 divided by 785,398 millimeters squared gives us 0.056 MPa. Okay, wait a second. Me and heels was 0.04 MPa. I somehow equal the same amount of stress as an elephant? What? This is unacceptable to me. But stop and think about what stress is. It's not about the specific force, and it's not about the specific area. It is about those two things related to each other. Let's talk about what happens if that elephant goes into my closet and picks out 4 pairs of my heels. So what if the elephant wears heels instead? So what if the area instead is 4 times our 100 by 75 millimeters? So instead of two of them, we've got 4 of them, but 100 times 75 was the area of my high heels. So let's see what happens for the elephant with this. That area is 30,000 millimeters squared. We've got 44,000. The weight of the elephant hasn't changed, but now it's wearing my high heels. And we've got 44,000 divided by 30,000. We've got 1.47 MPa. So the elephant, as you would imagine, with the same surface area, actually it's twice the surface area, has much more stress exerted on the ground than I do in high heels. So that's one of the great things. We don't have to worry about what the big object is if we can break it down to the elemental level. It's going to make talking about material a lot easier. Let's take a look at the next slide, because I think the next one's a calculation too. All right, let's do another stress example. Sorry, guys. Ugh. All right, what if somebody tells us steel can support 350 MPa of stress? They haven't said the word stress, but they've told us MPa, so we know we're talking about stress here. What force can a 25 by 25 steel cube support? All right, so let's take a look at this now. Let me make my screen big. All right. We have a cube of steel, and they've told us that that's 25 millimeters, and that's 25 millimeters. And we want to know what force P that can support. But they've told us that the stress can be up to 350 MPa. We want to know what the force is. We can calculate what the area is. It's 25 by 25, which we know is 625 millimeters squared. We know that stress equals force divided by area. Well, what we want to know is force. So force equals stress times area, or 350 MPa times 625 millimeters. Let's calculate this. 350 times 625 equals 218,750 newtons. So this is the thing. As much as I've said we like to talk about stress in newtons and millimeters, we like to talk about force in kilonewtons. So we're going to convert this back to kilonewtons, which just means we divide it by 1,000. So it depends on what way you round it. Some people round to the even, some people round to always going upwards, but 218.8 kilonewtons, or 219 kilonewtons, I'd be okay with that. But in assignments, I always give you a pretty explicit answer, and I always put in a buffer for a rounding error. I always build that into the answers in Quercus. Don't worry about that. So look at this. We took what we knew about stress and related it to a structural problem. Look at this little kind of tiny block of whatever here. Reminds me very much of our little block in our foam objects. I'm just going to go back and check the sound on some of those first ones. Okay, the sound wasn't as good as it normally is, but it did seem to be fine. And now the mic is in the right spot, so the sound quality definitely improved. Okay, so let's go on to the next topic. So that was stress. Let's talk about strain. So strain is the relative axial deformation of an element subjected to axial load. Now, we don't care what that axial load is. Something is causing this deformation, but for what we're talking about with strain, we don't care what that load is. We know it exists, but it's irrelevant to what we're talking about. What strain is the relationship between how much it deformed and what its original size was, or what its original shape was. So strain is it's actually millimeters divided by millimeters. So technically it's unitless. You might find it helpful to always write strain as millimeters divided by millimeters, just to help keep your head in the right place. Specifically because it'll remind you what units you're working in. You don't have to write units. Strain is a unitless element, so that is totally fine. But I find it helpful in the early stages to write strain as millimeters divided by millimeters. This is our symbol for strain. We know that this symbol means delta, or change. So that's the change in length. So not what the final length is, but what the difference between the original length and the final length was. This is the original length. So delta L is the final length minus the original length, or our axial deformation. And LA is our length after applied load. This one people have a hard time getting their head around, so I find a visual or an image helps with it. Let's take a look. Here is our original length object. So here's our original length L. Here's our force. We don't care what the force is. It's irrelevant. And it deforms this much. So it got this much longer. This is our final length. So our delta L is our final length minus our original length, or just this amount, this difference, this change, this delta. Strain is delta L divided by L, or our change in length divided by our original length. Let's take a look at another example. What happens if we have half the length, but we have the same amount of deformation? So this deformed the same amount. Delta L is the exact same, but our original length was half the amount. Delta L divided by half of L is 2E, or twice the strain. We have our original object with a delta L, and so strain is delta L divided by L. What happens if we have half the original length and half of the first example's deformation? So half of delta L. We have half of delta L divided by half of L. These two things have the same amount of strain on them. So let's do an example. Okay. This is where I always say, everything you need to know about structures, you already know. Strain is a hard one to find an example of, so I really like this example. There's no math in this example because I just want you to get your head around it. We will do some strain examples, don't worry. All right, I love this. Sometimes Dave's in the room when I do this lecture, and I really love it because I have a picture of him one time wearing an absolutely ridiculous mustache. It's taken in the summer. Dave was feeling pretty good, and he put on his running shorts. Normally I say swimsuit, but because we just had that weird thing with him in running shorts, Dave's put on his running shorts, and he's feeling fit and trim. He's been running, he's been working out, and they fit perfectly. He pulls them up, and they just fit perfectly on his waist. That elastic doesn't stretch at all. So here are the shorts. It's now the fall. You know, we didn't get out as much, drank a few beer, ate some Halloween candy. Dave pulls on his running shorts, and you know what? They're a little tight. They stretched a little bit. Well, winter holidays come around. Dave has been eating a lot of junk food. He goes to put on his running shorts. They stretch that elastic a lot. Let's take a look at what's happened here. They all started at the exact same length. Holding them in his hands, that elastic band is the same length in all three scenarios. In this one, the elastic band doesn't stretch at all. In this one, the elastic band stretches some, and in this one, the elastic band stretches a lot. No delta, some delta, lots of delta. So this one has no strain because there is no delta divided by the original length. It's 0. Some delta divided by the original length. We'd get some small amount of strain. Lots of delta divided by the original length, we have an increased strain. So intuitively, you know, he's straining the elastic on this one the most. Okay, let's do some, I'll just do this example verbally because then we go back into some slides. Okay, we've got our same cube of steel, but this one is, we've also listed that this is 25 millimeters tall. So before we were talking about 25 by 25. Now we're talking about one that is 25 millimeters tall, and there's some load on it. We don't know what that load is, and it deforms 1 millimeter. So it was 25 millimeter, and it deforms 1 millimeter. Does it stretch or does it compress? They haven't told us. They've just told us that the delta is 1 millimeter. And we're going to talk about that in a little bit. And in fact, I believe I give you a question on the assignment specifically related to that. Okay, so we have 1 millimeter is already the delta. So 1 divided by 25 is 0.04 strain. Remember, it's millimeters divided by millimeters, so I have no unit here. Some of you might find it handy to keep putting millimeters divided by millimeters there. Just as a reminder, if you're one of those people that likes keeping track of your units because it helps you track the math problem, go for it. I fully support doing that. Okay, you guys know all of these weird things I'm talking about. It makes sense. Some of it's obvious, but why would we talk about this? You could just do some of this little math. Why wouldn't we just keep things in force and deformation? Why would we bother with stress and strain? Why would we break it down to the material level? Well, objects are easy to manage. Buildings are gigantic. When we're talking about buildings, we're talking about very small movements. Movements you can't see with the naked eye. So, if this is our unloaded building and this is our loaded building, if you even took this with a ruler, you'd have a hard time noticing what this difference is. So it gets really hard to talk about it in a building size state of math. And how do we test this? How do we know if this works or not? Do we build, if we want to build a skyscraper, do we build one skyscraper, test it until it fails, and then build the next one? No, we need something that we can test at a small scale that will give us the answers that we can then extrapolate to design our big building without having to design a big building. So it's really hard to test full-scale elements. Knowing the part behaves like the whole means we only need to test little tiny objects to understand the material. Now, there's different ways to test things. What we'll often do is a coupon or a dog bone test. So we take a piece of material like this and we'll stretch it and we'll measure how much it deforms and we'll measure when it fails. And so there's different ways we track this information. Because remember in the first lecture and then also in the first lecture, Structures 1, I showed you that graph when Cast Connects was testing their steel objects, and it would track how much force and how much deformation was on an object. Well, we'll often convert that into stress and strain because we know how much force we're putting on and we know what the size of the object is. We can convert that to stress and strain very easily, and we'll call those stress-strain diagrams. And stress-strain diagrams are really handy for understanding material behavior. Okay, when do these stress-strain rules not apply? Because they apply in our world the majority of the time. But as I always say, most of the things we're talking about are typical conditions. So for us, that's almost always. But when doesn't it apply? Well, phase changes. When we jump from, liquid to gas or solid to liquid, the rules change. There is a fundamental change in the material behavior at that point. Extreme temperatures, the rules change a little bit. and extreme stresses and strains. Like I'm talking really extreme stresses and strains. So what might that be? So a phase change, ice hotel evaporates. Extreme temperatures, steel in a fire. It changes the way the steel behaves. Extreme stresses and strains. The best example I could think of would be in a black hole, for example. We understand that in these applications, the way we analyze buildings normally would be different. Okay, here's where it gets really cool. The relationship between stress and strain has a name. Remember I said there was some force that we're applying to when we calculate strain, but we don't care what it is? And that's true when we're talking about the strain. But that stress and that strain are related to each other. And in the realm that we're talking about, we call it the modulus of elasticity, is a measure of the stiffness of a material and is defined as stress divided by strain. So E is the modulus of elasticity. Depending on the material, we might call it the Young's modulus. We know stress is in MPa and strain is in millimeters per millimeters or unitless. If we have MPa divided by a unitless number, that means our modulus of elasticity is also in MPa. What I love about modulus of elasticity, if we know what stress and strain are, we can start to do really cool things with it. And this is really handy because we, with a coupon or a small element that we can test, we can predict, we can calculate the modulus of elasticity of a material. That can be a known thing for us. It isn't some abstract thing. If we know what the material is and we've tested it, we know what E will be, which means now we have a way to talk about stress and strain together. And we know stress is force divided by area, and E is the change in length divided by the original length. All of a sudden, there's some real things we can do here. So, modulus of elasticity is stress divided by strain. Stress is force divided by area. And strain is delta L divided by L. That means, well, E is force divided by area divided by delta L divided by L. That's cumbersome and awkward. Let's rearrange this and make it a little bit easier to look at. E equals PL divided by delta LA. So, if we know this based on the material, and we know what force we're applying, and we know what the original length of an object is, and it's an object we're picking, so we know what the cross-sectional area is, we should be able to calculate how much it deforms. Oh, that's handy. It seems like we have some things we can work with here. We could rearrange this depending on what things we know and what things we don't. So, knowing length and area, because we're setting that out in our building, we can now calculate the force or the deformation. And for common building materials, we know the stresses and strains in their normal range. If we know the member, we can figure out what load it will fail at, or what size member we need to make sure it doesn't fail. So rearranging for the thing we might want to know, this is all four of these equations are the same equation in the last slide, just rearranged for the thing we might want to know. What can we do with this? So let's see. Let's take a look. Well, first let's talk about modulus of elasticity for different materials. I said that for different materials, we know what that is because we have a lot of really smart people doing a bunch of tests on those things. I've done tests on them. You guys have the unique advantage of having a TA who is in structural engineering, and I guarantee you they have done a lot of these stress strain analysis. They have probably done a ton of them. I haven't spoken to them explicitly about it, but I looked up a lot of their work, so I know you have somebody you can talk to about stress and strain. Okay, so common modulus of elasticity for some of the materials that we use a lot. Structural steel, 200,000 MPa. Stainless steel, 180,000 MPa. Aluminum, 69,000 MPa. Brass, we don't use that much. Concrete has a huge range. In fact, I don't like this slide. I'm gonna update this slide here for concrete and wood and give them a range. And I'm gonna put an asterisk beside them because those ones are not very consistent. Wood has a ton of different values. Concrete has a ton of different values. It depends very much on the strength. So concrete has a little more play in what's happening there, but we'll talk about that in some of the later lectures in the term. Steel doesn't change. 200,000 MPa. I mean, that's not true. There are times where steel has a different modulus of elasticity. If we're talking about cables, for example, there's stainless steel, but those are basically different steel. Normal structural steel has a modulus of elasticity of 200,000 MPa. It's the only one I'm going to make you memorize. Now, I give it to you all the time. We're going to say it 100 times throughout the term, but modulus of elasticity for steel is 200,000 MPa. All right, let's do an example here. In fact, we're going to do a couple examples, so I'm going to turn my camera down. Like this. Move my chair. All right, if our 25 millimeter steel cube deformed 1 millimeter, what was the force on the cube? So we had our strain example. So here we go. I'm going to make sure you guys can see this. So we still have our 25 by 25 by 25 cube. So that's 25 millimeters. And that's 25 millimeters. This is 25 millimeters. And they have told us that this has deformed 1 millimeter. So they've told us that delta L equals 1 millimeter. We know what our area is. It's being applied over this area, so we know it's 25 by 25, or 625 millimeters squared. We know what the original length was. It's 25 millimeters. And we know what the E of steel is. It's 200,000 MPa. That is something I have given you. That is always going to be a known. We want to know what that force was to make that move 1 millimeter. So we know, if we go back to our slide, well actually we can rearrange it. E equals PL divided by delta LA. My slide is missing the delta there, so that is slide 28. We can rearrange this to find what P is. P equals E times delta LA divided by L. E times delta L times A divided by L, or 200,000 times 1 millimeter times 625 millimeters squared divided by 25 millimeter. I'm not going to put the units in there. I didn't for the rest. We can plug this into our calculator. 200,000 times 1 times 625 divided by 25 equals, wow, 5 million. Except we know it's 5 million newtons. Once we're talking about force, we like to talk about it in kilonewtons, or 5,000 kilonewtons. Hey, do you guys remember where it said that our steel cube can only take 350 MPa, and 350 MPa meant that it could take 218.9 or 218.8 kilonewtons, it seems like this would overstress our steel cube because this would cause too much stress on our cube. Interesting. That seems like maybe this couldn't even exist, but that's a whole other problem. We'll talk about those things coming up. But I just wanted to show you a worked out solution here. Let's go. I think the next slide is also another problem. Okay, so that one steel cube to deform 1 millimeter would take 114 elephants. Right, so here, does it make sense? Stress told us max P was 218.75 kilonewtons. Okay, if the max stress our steel could take was 350 MPa, which meant 218.75 kilonewtons, how much can it actually deform? So this can't actually happen. I hadn't realized I had included this slide. It's one I've been meaning to add for years, so I'm really happy that at some point in the past, Shannon did it. All right, so we're saying that this is ridiculous. This can't happen because we know it overstresses this. So P equals 5,000 kilonewtons is greater than the P max that we could have of 218.75 kilonewtons. So this is nonsense. This can't happen. It would overstress it because this means our stress is greater than our stress max. Because remember, this was the maximum stress we could see, was 350 MPa. What if we knew that the maximum force we could have was 218.75 kilonewtons? Okay, so max P equals 218.75 kilonewtons. And this is because the stress max was 350 MPa. So this came directly from this. We did this calculation ourselves. All right, our L is 25 millimeters. Our area is still 625 millimeters squared. The E of steel is 200,000 MPa. And P is 218.75 kilonewtons, which we know if we're working in newtons and millimeters, we need to switch this back to our 218,750 newtons. And delta L, we want to know how much this would actually deform under the maximum stress it could possibly see. E equals PL divided by delta L A. We want to rearrange this for delta L. Bring that up here, bring E under. PL divided by EA, or 218,750 newtons times 25 millimeters divided by 200,000 MPa times 625 millimeters squared. Delta L equals, okay, let's plug this into our calculator, 218,750 newtons times 25 divided by 200,000 divided by 625 gives us 0.04375 millimeters. So the maximum stress applied to this block, which is how many elephants? 218 divided by 44. 5 elephants is the amount of load this one little block of steel can take. That's the maximum force it can take. But that's a lot of force. 5 elephants standing on that block cube is the maximum force it can take, and even then, it deflects less than a millimeter. And this is why it's so important to understand the material level of what we're talking about. Because being able to test full-size objects becomes impossible, because such a high load results in such a small amount of deformation. And so we need to understand what these things are on an elemental level to be able to talk about them on a large scale object. Okay, let's make me smaller. Here we go. Okay, so we did that out here. Oh, we have another example. We have one more example, and then we'll talk about stress-strain curves. And then hopefully I can get this posted for you guys. At least not too late. Again, I apologize that everything is so behind. Okay, this particular rubber has an E, or a modulus of elasticity, of around 55 MPa. How much load does it take to deform a 25 millimeter cube the same 1 millimeter? We don't know what the maximum stress this can take, but have any of you ever played with those round, hard balls? The old name I know for them is inappropriate. You would use them in floor hockey, for example. They're quite hard, but they are a rubber ball. It's a very stiff rubber, but you can deform it. And you know that you could deform it 1 millimeter if you needed to. So let's take a look what it would take for this rubber cube. So let's make my math bigger for you guys here. All right, so we've got this rubber cube. All right, and we know it's 25 millimeters by 25 millimeters by 25 millimeters. We know that the original length then is 25 millimeters. We know that the area is 625 millimeters squared. We know that the E of rubber, of this particular rubber, is 55 MPa. So remember, steel is 200,000 MPa. So this is drastically less stiff. And we know our delta L is 1 millimeter. We want to know what force causes that 1 millimeter. Okay, so P equals E delta L A divided by L. I had already rearranged it up here, but I could take the time to rearrange it on my own if I needed to. I have also rearranged all of these for you in that slide earlier. So we have 55 MPa times 1 millimeter times 625 divided by 25. You can plug this into our calculator. 55 times 1 times 625 divided by 25. We get 1,375 newtons. We know that once we're talking about force, we like to convert it back into kilonewtons, or 1.375 kilonewtons. You can see why I always tell you how many decimal places to put and what units I'm looking for my answer in, because you wouldn't know in a particular question if I was asking for newtons or kilonewtons. And Quercus Quarkus is great, but it has its flaws that it has to be very, very explicit. It doesn't give me the opportunity to go through and review the things. Okay. So that's worked out here. All right. Let's talk about stress strain curves. I wanted to add. Let's talk about stress strain curves. So this is that plotting of testing a coupon. Now, we don't care what size it is. It could be whatever size possible. We don't care because we're talking about how it behaves no matter what size it is. We want to know the stress versus the strain. It should look the same as some force being plotted against some particular area. If we know what our object is and we're the ones applying the force, we know its original length, we know what its length is changing, how its length is changing for each particular load, because we're the ones applying the load and measuring the change. In a lab environment, in a very controlled place, where we can convert those into stresses and strains. So stress-strain curves describe the behavior of a material under a wide range of stresses. The shape of the stress-strain curve defines a number of properties about the material. And so these are very, very handy for us to talk about. Okay, stress-strain curve. The strain is on the x-axis, the stress is on the y-axis, and the slope of this line is our stress divided by strain. If you guys remember, the slope of this line can usually be defined for a lot of things, and for us, it gives us a really handy bit of information. In its linear elastic range, this is going to be a handy thing to know. Okay, I'm going to show you some graphs, and you're going to hear me use some words. These words are important. I want you guys to know these ones. We're going to talk about them a lot. And again, these are all words you already know. So stop and think, if you're like, I don't understand how this applies, stop and think how you remember using it in the past. Take that word and apply it to something, and then see if it relates to the definition I'm going to give you. Because like I said, everything you need to know about structures you already know. And these are all words you've used at some point. So elastic, the tendency of a material when unloaded to revert to its original shape in the opposite manner to which it became deformed. For those of you that have one, grab a paper clip. Where are all my paper clips? Have my children taken all of my paper clips? I normally, in person at the beginning of this lecture, hand out to everyone a paper clip. And I usually have a thing of gigantic paper clips. I only have these rubber-coated ones here right now. That's fine for me. For you guys, if you can, go try to find an all-steel paper clip if you have one that you don't mind destroying. Okay, I have to use this rubber-coated one because it's what I've got in my hand, but it's steel inside this. So when you've got a normal old paper clip like this, it's perfect, it's pretty flat, there's been something done to it. If I take this and I have, this adds up to 2, 4, 6, 8 sheets of paper, and I put it inside my paper clip has deformed somewhat. There is deformation there about the thickness of that paper. I pull the paper out. My paper clip goes back to its original shape. That was elastic behavior. You guys tend to think about it with an elastic band because you intuitively understand that it goes back to its original shape, and that's elastic. Plasticity is the deformation of a material undergoing non-reversible changes of shape in response to applied forces. Not all materials have this. Concrete does not have a plastic zone. Wood does not have a plastic zone. Steel has a fantastically beautiful plastic zone. So let's test it with our paper clip. I'm going to fold this paper up to something really, really thick. So this is a nice thick stack here now, and I'm going to take my paper clip and I'm going to stretch it, and I can get it over that paper. Look, it's done it, but when I take it off, look at that. It's got permanent deformation. We know with a little bit of paper, it snapped back to its original shape, but this time it didn't. It had permanent deformation. But it didn't fail. It's not a broken paperclip. It doesn't do its original job, but it had plastic behavior. There is a deformation there that did not result in its ultimate failure, but it has permanent deformed shape in it. Here's the really cool thing. I'm going to bring it back a little bit to slightly less deformed permanent shape. If we put permanent deformation in a thing, so watch this. It's hard to see on my little camera, but if you're doing it here, get it to a point where it deforms your paper clip some amount, but when you pull it back, you can see that it snaps back some, but it has permanent deformation still. It will still snap back the same amount that it did in the first version, where it was all elastic behavior. But the plastic behavior was so much more that sometimes it's hard to see. But there will always be some amount of reverting back to its original shape, but there will be some permanent deformation if we get into the plastic zone. The yield stress is the point at which a material transitions from elastic to plastic behavior. So that zone, just where we switched, where something interesting happened to our stress there. I'm going to tell you that it's called the yield stress. You don't really know what that means yet, but for you, we will see it in our stress strain curves, but it happened at that point where we stopped having only elastic behavior. Ductile, a material which will undergo large permanent deformations, thereby absorbing a great deal of energy before failure, is ductile. A material which is not is brittle. So a ductile material can undergo large permanent deformations. Concrete doesn't have a plastic zone, therefore it is not ductile. It is brittle. Wood is brittle. So our steel paperclip, look at this. Look at that permanent deformation. That was far surpassed the small amount of elastic behavior we had. I'm going to tell you that in steel structures, we like to keep our steel in the elastic zone, in that tiny, tiny little range where it snapped back to its original shape. We try really hard to keep it in that zone. The difference is seismic design, for example. Did you see how much that did? Do it back and forth a few times. Just go back and forth with your paperclip and then touch where you were doing it. It gets a little bit warm. Your lip is more sensitive. I've got a rubber coating on mine, so it's hard to tell. But it heats up. It's absorbed energy. So it's taken some energy and turned it into something else. And that is really handy for things like seismic design. We really like that ductile behavior of steel, which is one of the few materials we work with on a structural scale that has that behavior. Ultimate stress, the maximum stress that a material can sustain. So maybe I keep deforming this paperclip. Oh, look at this. I've gone around like 5 times. This plastic. Oh, there. I failed it. The ultimate failure, the ultimate stress. There was some maximum stress that that material could sustain. But did you see how much permanent deformation I put into that object before it failed? Okay, there's some more terms here that I don't quite care so much about, like the proportional limit. It's the maximum stress, which the material behaves in a linear elastic manner. Strain hardening, strain softening. Those give us some weird blips in our stress strain curve. Not that much for you to worry about, but engineers can do cool things with those. Explicitly when it comes to using it in relation to seismic design. The elastic limit, the maximum stress that a material can sustain without going permanent deformation, and fracture strain, the strain at which fracture occurs. We have a few more. Strain energy, the amount of work done in deforming an object from its original shape. That's the area under the stress-strain curve. The elastic strain energy, or the modulus of resilience, is the amount of strain energy which is stored as potential energy and is re-released to springing back to the object original shape. Plastic strain energy is the amount of strain energy which is absorbed by an object undergoing permanent deformation. This is the one that all of the seismic focused engineers really like. Modulus of toughness, the total strain energy at rupture. So what's the total amount of energy that's gone into this? How much energy was absorbed by this paperclip before its ultimate failure? Okay, let's look at a stress-strain curve of concrete. This is a compressive stress-strain curve, and it's idealized. It doesn't look exactly like this, but this is how a lot of engineers will look at it. I'm doing a compressive stress-strain curve because concrete, the stress-strain curve for tension, is practically zero. We tend to think of it as having zero capacity. Did his headphones die again?
What's that?
Did his headphones die again?
No, he asked me to turn them off, so I just plugged it.
Oh, okay. All right, here's the stress-strain curve of concrete. So somebody took a block of concrete and put a compressive load on it, and they measured it. So right here, they put this much load on it, and they measured how much it deformed. And then they turned that force into a stress because they knew what the cross-sectional area was. They knew what the original length was and how much it deformed, so they could calculate the strain. And they did that again and again and again until they could plot this curve. Now, I know you're saying, that's a straight line, Shannon. That's not a curve. Except it is, even a straight line is a curve, I guess. And we will start to see that some of our stress-strain curves don't look quite so neat and tidy. And in fact, this one actually isn't this neat and tidy. This is the idealized version of it. Look at how tiny these strain values are. They start to get very, very, very small, and that's why keeping track of how many decimal places you have is very important. The E for concrete is widely varied, and it depends on what the makeup of the concrete is. Engineers have relationships for calculating E in relationship to the compressive resistance because it's all dependent on the mix. We're not going to worry about that too much. I'll usually give you what E is for a particular concrete. And look at this. They applied load and checked the deformation, applied load, checked the deformation, and they did it up until this point, and then it broke. Anywhere along here, had they taken the load off, it would have reverted back to its original shape. There would have been no permanent deformation. Up until it failed, and that was its ultimate stress. The area under here was the energy that went into failing this object. Elastic zone, no plastic zone because it's brittle. It was not ductile. It has no plastic zone. It was only an elastic zone. It's a little bit trippy to think of concrete as being elastic, but everything is elastic unless it's also got ductility and has a plastic zone. It might have a very small elastic zone, but it has an elastic zone. Okay, the partial stress-strain curve of steel. Steel's the exciting one. This is the one that's going to give us some answers here. Okay, let's take a look. This is the stress-strain curve of steel. We'll focus a little bit on this kind of little rounded zone, but not too much. I am sure that your TA is going to freak out about some of the ways I gloss over this zone because they are very focused on really good engineering. They're gonna have a hard time wondering why I've brought it down a notch or two. And I can tell you that for engineers, it doesn't look quite as simple as this. I've gotten rid of a funny little blip here. There's a lot that I have tried to do to simplify this, to have this conversation with you. But for the most part, this is a really easy way to talk about our steel stress strain curve. Here's our stress that's been calculated by how much force we've put on it. What are you looking for?
Breadcrumbs.
Breadcrumbs, other cupboard, this one right here. Behind that red box, see where all the paper, see where all the chip clips are? Chip clips right in front of you? Those are breadcrumbs. They're panko, but
Yeah.
same thing. Sorry about that. Actually, while I have an interruption, I'm going to say one thing. Would you do me a huge favor? David?
Yeah.
Could I have some water?
Sure.
So we can calculate what the stress is because we know what our object is. We know what our cross-sectional area is. We're testing this object. We know how much load is on it because we're the ones applying the load. We know how much it's deformed. It's empty because it fell over. We know how much it's deformed because we're measuring how much it's deformed, which means we can plot these things against each other and calculate E. Yield, or in steel, for different materials, we will call these values specific things. We have our yield stress and our ultimate stress. Some materials don't have a yield stress, and for each material, we tend to give it a specific name. For steel, we call it Fy. I think it's because it was really hard pre-computers to always write in Greek objects or Greek letters. You can imagine trying to, like in early typewriters, plop in a Greek letter into your writing. So they converted it to Fy. So yield stress, or Fy when we're talking explicitly about steel. You're going to see that when we talk about concrete and when we talk about wood, we change that symbol a little bit. Now, if this is our yield stress, and this is the maximum stress we want it to see, anything along here is okay. If we have 150 stress on our steel, it's great. We know we'll load it up, and if we unload it, it'll go back to its normal shape. We don't care. All the way up to here. If we load it up to here and unload it, boom, it'll go back to its original shape, and we are all very happy. After this, look, our strain increases even though we add no more force to it. It starts to deform. If we unload it, it won't go back to its original shape. Let's take a look. Don't worry about proportional limit. Okay, let's look at loading and unloading. All right, this red line, we've put a load on. It stayed in the elastic zone. We unloaded it. It goes back to its original shape. Perfect. Load it. That is the elastic strain energy, or modulus of resilience. It was able to return back to its original shape. It's resilient. There is, in fact, a whole field of study on resilient materials. Materials that can undergo large-scale deformations and revert back to their original shape. What happens if we load it up into this zone? So we load it up to here. We now have gone into the permanent deformation zone. If we unload it, it will rebound some. There will be some amount of resilience, but there is also going to be permanent deformation. So look, if we unload it, we've put the load on, we don't know what the cross-sectional area is, but we know that we put 300 MPa of stress on this object. And then we unloaded it. There is some permanent strain, meaning there is some permanent deformation in this object. There's no load on it anymore, but it has permanent deformation, just like our paper clip did. This was the amount it rebounded, or the elastic strain energy. This was the energy that reverted back to its original shape. This was the plastic strain energy, or the amount of energy that went into its permanent deformation. That is our residual strain. we can load it and unload it, and it will keep doing that. And if we did that cycle 4 times, we are going to have this much permanent strain in it. Elastic strain energy, plastic strain energy. So we'll always have, no matter what, we will always have the same amount of elastic strain energy, but we can increase the plastic strain energy. Okay, this is the full stress strain curve. You should be able to recognize this diagram. I love this on an exam. I guarantee you this image will be in your exam with 5 things that you have to match with 5 other things. So there'll be labels on it that you have to match with 5 other things. Hot tip, they're all in this slide. You do this, you're gonna get 5 points on your exam, no problem. Okay, this is what I already showed you. This is as far as we went. Now look at this, I'm using 300 MPa steel. There is different grades of steel. We tend not to work with 300 MPa steel anymore, but when I started, you had to specify 300 or 350 MPa steel because both were available on the market. So here's our modulus of elasticity, here's our strain, here's our yield stress. So those are the things we already talked about in our last slide. This is what the rest of the stress strain curve looks like. Look at this. There's like a weird thing that happens here where we start to be able to take more stress in our object. So it actually has a maximum stress that's higher than our yield stress. Well, that's kind of lovely. If we set our yield stress as the maximum we ever want to see in a building, but we know that it can take a little bit more stress than that, we've got a buffer built in for us, which is really handy. Now, there would be a lot of permanent deformation because look at everything that happened here to get to that. So it's not great. We don't want to have to do that, but maybe we can isolate that into specific spots to absorb a lot of energy. Okay, there's our yield stress. There's our ultimate stress. So we've got strain, stress, yield stress, ultimate stress, and strain at rupture. So that's when it finally ruptured. This is the maximum stress it could take, but that isn't where it ruptured. It then dropped off load and ruptured as it kept deforming. So this, I can tell you, stress, strain, yield stress, ultimate stress, rupture strain, you're gonna get your 5 points. Okay, let's load this up to here and then unload it. Take that load off. There will be permanent deformation in it, but there was some rebound here. So some of the strain released, but there is some permanent strain in this object or permanent deformation. That was our plastic strain energy, and that was our elastic strain energy. At rupture, that's our modulus of toughness. That's all of the energy that went into failing this object. Okay, some common yield and ultimate stresses of some objects. All right, yield stress, ultimate stress. Look at this, brass, concrete, wood. I didn't list a yield stress because they do not have a plastic zone. When they hit the end of the elastic zone, they fail. Their ultimate stress is at the end of the elastic zone. There is no zone where we load it and unload it and it has some permanent deformation. And it hits the end of the elastic zone, it fails. They are brittle materials. So, structural steel, 350 MPa. Like I said, we used to work with 300 MPa quite a bit, but we don't anymore. I have a funny note here that says 345 MPa. In a couple weeks, we're going to talk about steel as a material, and I'm going to explain why sometimes we use 350 and why sometimes we use 345. And it has to do with how we heat it up when we make specific objects. Our ultimate stress is 450 MPa. Stainless steel has a higher ultimate stress, but a much lower yield stress. Aluminum, less yield stress and less ultimate stress. The difference between the yield and ultimate is very small in aluminum. Concrete, again, this value changes. This was just an example. These would be the worst stresses we would like our object to see in our design. So these we would often set as our maximum. If that's our maximum, if it's less than that, we don't care. What we really care about is knowing when it fails, because anything less than that, we're gonna be okay. So we'll often do our math using these maximum values, because if it's less than that, we know we're good. It's a thumbs up. As my son would say, 10 thumbs up. Okay, I have a video I want to show you. Normally I would talk to you through the airing of this video, but when I play it through while also recording and with the slideshow on, it causes a funny blip lag. So I'll give a little preamble, but what I really want you to take away is that all the things we've talked about, they show, and that in some ways they actually make it more complicated. They use some, it's a British version of it, so some things they call slightly differently, but it is the same thing as us. It's gonna be, they have it, I have this labeled wrong. I'm gonna fix the label on this because I added that label there. I have that labeled wrong. I have fixed this before, but not in this class, I guess. So for you guys, this will be fixed. It'll be stress and strain. And this is the stress strain curve. You can see that's the modulus of elasticity, or the E is the slope of that line. Oh, it didn't, it's not a hot link in there. So give me just a second to get this going for us here. Is it gonna make me, I wanna do it without it cutting out the lecture slide. See if I can do this. All right, give me just a second here, team. Kind of weird.
Waiters always look at me
This is gonna
and
have
think that I'm
an
gonna have
ad.
a salad, maybe a soup, and that'll be the whole meal.
Skip ads. Okay, let's pause this. I'm gonna bring that over to you guys in just a second. Okay. Here we are. Whole screen. Yeah, I know it seems weird that we're watching a video of me watching a video.
The tensile test. First test, material with yield point phenomenon. In the first tensile test, a plain carbon steel with yield point phenomenon is to be tested. This is the test piece. It has a cylindrical test region with an original diameter of 10 millimeters and an original gauge length of 100 millimeters. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand control.
So there you could see that we had an original length and original diameter. That original diameter means we can calculate the cross-sectional area. We know what area we're using, and we know what original length we're using. They're going to use this machine that will measure how much it deforms and how much load they're putting on it, which means at any point we can calculate the stress and the strain on it.
The tester moves the upper crosshead into its correct starting position. Now we can place the threaded ends of the test piece in the lower and upper grips of the testing machine. In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary testing parameters on the control computer. Ready. The test starts and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 millimeters. During the tensile test, the test piece is slowly and constantly elongated with a standardized speed. The force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer display. The material behavior can best be observed in a force elongation diagram. The force F is being plotted upwards on the vertical axis, the elongation delta L towards the right on the horizontal axis. At first, the force rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram. In this area, the material behaves elastically. If the test piece were to be unloaded from this area, it would spring back completely to its original length. In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be unloaded now, it would not spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the Modulus effect. After a certain strain, known as the Modulus strain, the force increases again. The material opposes an increase in force against the imposed elongation. It strain hardens. Up to the point of maximum force, the test piece is strained uniformly along its length. This means that the test piece gets longer and thinner, but keeps a cylindrical shape. As soon as the maximum force is reached, a neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece fractures there. In the recorded force elongation diagram, the force FEH at the upper yield point can clearly be seen. This is the highest force the test piece can sustain elastically. FEL is defined as the force at the lower yield point, Fmax as the maximum force. Using these forces, the strength properties of materials can be calculated. The upper yield strength REH is calculated by dividing the force FEH by the original cross-sectional area S0. The lower yield strength REL is defined in a similar way. The maximum force divided by the original cross-sectional area is called tensile strength Rm. In the last step, the tester swings the extensometer back into its resting position and removes the broken test piece. On the work table, he puts the fragments back together again. With the help of the distance marks, the percentage elongation after fracture can be determined. This is the permanent strain after fracture and amounts to about 30% in this example. Please note that the percentage elongation after fracture depends on the length to diameter ratio. By measuring the smallest diameter at the point of fracture, the percentage reduction of area can be calculated. It describes the reduction of cross-sectional area at the point of fracture in relation to the original cross-sectional area. In the second tensile test, a material without yield point phenomenon is to be tested.
Let's just jump ahead to the actual test here.
The initial linear curve in the force elongation diagram again shows the elastic behavior of the material. But this time, the end of the elastic area is not revealed by a sudden drop of force or any distinct change. there is a smooth and gradual transition from linear elastic behavior to plastic deformation. In the further course of the tensile test, the force increases and the test piece again is strained uniformly along its length. At the point of maximum force, a neck develops, and all subsequent plastic deformation is confined to this neck until fracture finally occurs there.
Okay, that's as much as I wanted to share with you guys about that. Mostly I wanted you to hear the things that I was talking about in someone else's voice. So they used all the same terminology. They plotted that force elongation. They could change that force to stress, as you saw easily, and they could change that deformation into strain because they knew the original bits of information. So it's very easy to calculate that. In fact, a lot of those sensometer tests will do that embedded. If you input what the original information is, instead of even plotting it as a force elongation, they will actually plot it as a stress strain for you. So it's just kind of embedded in the hardware/software of it. So you can see that those were large forces. That's a very expensive machine to test it. I have done large scale testings in a lab, and it takes a long time. I remember that we had a PhD student when I was doing my undergrad testing a concrete slab with a specific GFRP reinforcing. And it was a 3-month testing process because it was such a large scale and they were trying to measure so many different things over a long scale process. And we thought we knew when it was going to fail. In fact, we all gathered around one day and it didn't fail that day. It took 2 more days until it finally failed. And it was a big celebration because that thing had been taking up our testing lab. And when I say our testing lab, it was gigantic. It was the size of, I wish I could remember how large it was, but it was, the testing facility was 2 stories high, definitely bigger than my entire house, bigger than, not as large as the auditorium room at the school, but not far off of one Spadina's big room. Not far off of that, I would say. So a really large thing being tested. And there's other things going on in around it as well. Okay. All right. I want to quickly touch on shear because we're not going to spend a lot of time talking about it, but you need to know what's going on. And there's some other things that we're not going to analyze that we're going to use some terminology from later in the term. And I just want you to know that I didn't just make it up and pull it out of nowhere. It came from something, but it's beyond the scope of this course. So we know that shear is that racking force. Now in this image, it's shown this way. So you can see that my object is racking this way. So I've got it slipping past each other like this. But when it deforms like this, we can see that it's actually also racking in that direction. So those two planes, it's a lot harder to do it this way. These 2 planes slipping past each other this way, if we do it here and here and here and here, as they slip past each other, it causes the other 2 sides to skew as well. And we end up with internal forces that look like this. These can be rewritten as for you guys, these 2 compressing and these 2 in tension from each other. So you can take those shear forces and rewrite them as principal forces at a 45 degree. So shear and its equations, we're not going to worry about this. I just wanted to show you that this idea of stress and strain for axial loads applies to shear loads as well. We are not going to analyze these, but I want you to know they exist. And I want you to see that they look similar. So this is our average shear stress. it's equal to V divided by A. Well, V is shear. So instead of force divided by area, we've got shear force divided by area, and that's our average shear stress. This is an angle or a shear strain, and this is our skew angle divided by our original height. So this looks very similar to our strain formula, but for shear. And this is G. It is our shear stress divided by our shear strain. So this G looks very similar to our modulus of elasticity. So it's our shearing modulus of elasticity or modulus of rigidity. You do not have to know these. I don't need you to memorize these. You don't need to know these. But I wanted to show you that these equations look almost identical to our axial ones. So do they look familiar? Look at these. These are our axial ones and here are our shear ones. They are almost identical to each other. They are all terms related to shear instead of axial, but they follow the same pattern. G is going to come back to us later in the term when we talk about steel. You're not going to have to know it, but I want you to understand kind of where it did come from. You don't have to know, but I just want to tell you for those that ask, because inevitably I always get asked this question. So G is not something we're going to talk about very much, but I wanted to show you where it comes from. There is a relationship between E and G, and this is what it is. It is this funny little V or Poisson's ratio. In strain, when we were squashing our object, we only talked about how much it deformed. But that deformation went somewhere. Our object would bow out, and I like to use my eraser to talk about this the most. When I squash my eraser, I can squash it. If I feel right here, I can feel that it bowed out some bit on the sides. So again, you don't need to memorize this. I'm not going to test you on it, but I want to show you what that is. You can see how it bows out here. Well, this is our Poisson's ratio. It's the ratio of lateral strain to the longitudinal strain of a member subjected to axial loads. Don't worry about it. I just wanted to tell you that G comes from E, and there is a relationship here about this bowing and a skew angle, and they are all kind of interconnected to each other. Okay, here is the recap. I like this slide because it has all the equations all summed up for you. Stress is force divided by area. Strain is our change in length divided by our original length, and our modulus of elasticity is stress divided by strain. We can plug these into each other and rewrite it in any of the things that are going to be handy for us later on. Let's do an example where it looks like I already have the answer worked out. Oh no, we want to know the D required. Okay, we have some examples here. And I think we're almost at the end of the lecture. Yeah, okay, so this is the last example we're gonna do. Let me flip this down for you. All right, this is an actual example. We have a force applied to this column. They've told us the original height. It makes sense. We're designing this building. We want this column to be 3.2 meters tall. We're being told that there are 5,000 kilonewtons of force being applied to it. We have a limit. We're trying to fit this in something. We want this to be a specific width. We're being told that we've got to keep this to about 2 inches or 50 millimeters. We want to know what the D required is, or how deep does this member need to be. We've been told that steel, this is our maximum steel stress we want to see. If it goes over this, we're assuming it's failed. Well, look at this. They've given me this term here, reduction factor times Fy equals 270. We're going to talk about where this came from later in the term. I'm just giving it to you now. So instead of 350, I am giving you this as 270 MPa is the maximum stress we want to see on this object. Okay? So we know that our steel E is 200,000 MPa, and we've also been told the maximum deflection we can see is 5 millimeters. Okay, let's make me big, and we want to find out what the D required is. We know that for any object, we care about strength, stiffness, and stability. So axial example. That should have been drawn as an actual free body diagram, to the point that I'm going to go back and fix that for you guys. It bugs me that it's not an actual free body diagram. Okay, here is our column. We're being told that it has 5,000 kilonewtons of load being applied to the top. It's a column. They haven't told us this explicitly, but most columns, we know, have this free body diagram. They haven't asked us to solve any of that, but we know that we could go about this and solve what all the internal, or what all of the reactions are on this. They've told us that this is 3.2 meters tall. So we know it's stable because this would be connected to a beam or a column below or a foundation, and this would be braced by a roof or something at the top. So we've got a stable object. So check one. We need strength, stiffness, and stability satisfied. We know our strength limit is 270 MPa, and our stiffness limit is, they've said, 5 millimeters of deflection. So those are the maximums. So we want to know what this object needs to be to meet those. We've met stability because we've got a reasonable free body diagram here. Okay, they have said that the cross section of this object so there's our cross-sectional area. They've set this for us. That needs to be 50 millimeters. For some unknown reason to us, that's a very important dimension to them. And this is what we don't know. We want to know what that D, or that depth, needs to be. They have given us steel Fy equals 270 MPa, and they have given us the steel E equals 200,000 MPa, and our delta max equals 5 millimeters. So we only want this to squash 5 millimeters. We've been given a limit on that. We want to know what D we need to make this work. All right, so I always like to write out my knowns. So I know I've just written some of this already, but this is a really good habit to get into. So we know that P equals 5,000 kilonewtons. I'm going to rewrite this as newtons as well right now. It's a handy thing to do. H, we know, is 3.2 meters. We could call H L because that's the length of this object. I'm going to rewrite it as millimeters because we know when we start talking about stress and strain, we like these things to be in millimeters. B equals 50 millimeters. We often call this dimension of the object B. So that's how wide it is, and that's how deep it is. Fy, I am going to assume that this is what they're talking about with Fy. Oh, thank you for lunch. Fy, we're going to call this 270 MPa, or this is our, if you wanted, you could say this is our maximum stress. E is 200,000 MPa, and delta max, in fact, let's call this strain or stress max and call this delta max, is 5 millimeters. So that's how much we're allowed. That's the maximum we want to see. What do we want? We want D required for strength and D required for stiffness. They're separate calculations. We want to see what strength or what D we need to meet our strength calculation and what D we need to meet our stiffness calculation. This doesn't seem very, it's like it's trying to focus on my lap instead of the paper. It's a little bit blurry, so I do apologize for that. I have a good camera, I promise. Okay, for strength. For strength, we know stress equals force divided by area. We know that our Fy, or reduced Fy, is 270 MPa, so we've got that. And we know our area area equals B times D. So stress equals force divided by B. D is what we want to know. So let's rearrange this. D equals P divided by stress B. So let's plug this in. We've got 5 million newtons times 207, or divided by 270 MPa divided by 50 millimeters. Let's plug this into our calculator. 5 million divided by 270 divided by 50 equals 370.4 millimeters. So, to make sure we don't exceed the stress capacity of this column, we need this member to be at least 370.4 millimeters deep. If it's shorter than this, the stress will be too high, because remember, a smaller area means an increased stress, and if this is the maximum stress we can see, our object will fail. We know there's a whole thing with buckling that we're not talking about, but that's later's problem. Let's look at stiffness. We know that stiffness, or strain, A equals PL E delta L, because we want to find A here. This would be BD. We can just bring B over here. So we want D equals PL divided by BE delta L. $5 million divided by 50 and 200,000 MPa and 3,200 millimeters. D equals 5 million divided by 50 divided by 200,000 divided by 3,200. What did I do here? Oh, sorry guys. Look at that. This is supposed to be up here, and this is our maximum that we're allowed. So P is 5 million newtons. Our original length is 3,200. B is 50. E is 200,000 MPa. Sorry, I don't know if you can hear that screaming in the background. Delta L is the maximum deformation we want to see, which is 5 millimeters. We have 5 million times 3,200 millimeters divided by 50 meters divided by 200,000 MPa divided by 5 equals 320 millimeters. So, to meet our strength requirements, our our column needs to be 370.4 millimeters deep. And to meet our stiffness requirements, it needs to be at least 320 millimeters deep. If this was less deep than this, we would exceed our deformation. So which one is it? Which one do we use? Do we use our 370 or do we use our 320? Which one do you think? Yeah, we have to meet the criteria for both of these things. We need it to be strong enough, stiff enough, and stable. We met stability with our free body diagram. We have to meet at least 370 for strength and at least 320 for stiffness. So it looks like 370 is the way to go. Let's cross-check these. Let's see what deformation we would get if we use 370 as our depth. And let's see what stress we would get if we use 320. So let's check. Okay, let's do a little check here. All right. So, delta L, if we use 370 millimeters. So if D equaled 370 millimeters, what delta L do we get? Okay, so we know that the equation is delta L equals E times our length divided by E. I'm just going straight back to the original equations, times our area, which we know is 50, times 370. I'm going to use the 0.4. What does it matter? That's pretty close. So let's plug this in. Remember, we need this to be less than 5 millimeters, and we're happy. So 5 million times 3,200 divided by 200,000 divided by 50 divided by 370.4, and we get 4.31 millimeters. So our 370 meets both our strength and our stiffness requirements. Let's check stress if D equaled 320 millimeters. So what happens to the stress if we use the smaller dimension? Now you know, we talked about this when we talked about the shoes. Here's a quick gut check. If we decrease the area, does our stress go up or down? It's going to go up. So intuitively we know this should be higher than 270, which means our 320 isn't going to work for us. But let's just check that out. Stress equals our force divided by our area, which is going to be 50 times 320, or 5 million divided by 50 divided by 320 is 312.5 MPa. Is that greater than or less than our 270? Our 270 was the max. We were told that if we went over 270, this would fail. So no, our D needs to be 370.4 millimeters. Now, that's a ridiculous number. We wouldn't use that. We would probably use 375 or something like that. I would try to be very explicit in a question of what I was asking, whether it was the exact number or whether it would be reasonable to round up. But that is what we're doing here. We need these things to meet our strength, we need them to meet our stiffness, and we need to meet the stability. So let's make me small. Oh, look at that. I didn't realize you can see my children throwing couches around in the background. Okay. All right, so we worked through this problem. If you needed to, it's all worked out here. So you have a worked out paper version of that example as well as the video version of it. All right. Forever tips you should just get in your head Stress and strain relate to strength and stiffness, and stress and strain are related to each other. For this course, you should know the equation for stress, you should know the equation for strain, and you should know the modulus of elasticity and the typical steel values, steel stress strain curve and the first 2 slides of definitions, and you should understand the difference between elastic and plastic. Remember, elastic, it'll revert back to its original shape. Plastic means there will be permanent deformation. There are materials that do not have a plastic zone. So when we talk about concrete and when we talk about wood coming up in this term, we do not have a plastic zone. We only have an elastic zone. Steel has a beautiful plastic zone. And you should understand yield stress. So for steel, that's the point where it switches from elastic to plastic. Okay, so this was a lot of new information, I think, in this week's lecture. Next week, we're going to start talking about how these things apply to bending stress. And this is what's really cool. Okay, if we've got our object and we've talked about axial loads, what happens at the top of this? It is in compression. And at the bottom, it's in tension. And at the middle, it doesn't look like much at all happens. There's a shape change, but it doesn't seem like there's a length change. Remember, strain was all about how much it deforms, and it looks like the most amount of deformation or change in length happens at the top and bottom when we bend something. So that's going to be what we start to talk about next week.